Let's get into an exciting application called Torricelli's law. It concerns water draining from a tank. So, if we have a tank, like pictured, and it's full of water, then, and if we have a hole in the bottom of the tank, as I've drawn here, and the water drains out of that hole, it will drain out according to Torricelli's law. Torricelli's law states that the velocity with which the water is exiting the hole is given by this expression, the square root of 2 times g, where g is the gravitational acceleration, which we can take to be 9.8 meters per second squared, assuming these problems are taking place on Earth's surface, and depth is the, well, it's the depth of the water, which I'll refer to with the letter y. So more succinctly, Torricelli's law is given by this expression here. And if we read into this a bit, what it tells us, and by the way, just make sure you understand that this is referring strictly to the velocity of the water as it exits the hole. Of course, if the picture is as it's drawn here, it'll accelerate, but I'm referring to the velocity that it exits the hole. Now, if we're interested to know how fast the water is draining out of the tank, then we can talk about the rate of change of volume, capital V, and dV dt. If you think about it for a bit, it's the volume is decreasing at a rate equal to the area of the hole times the velocity with which the water is exiting the hole. Now, if that's not intuitively obvious to you, well, try thinking about it for a bit. Maybe it'll eventually click for you that the volume of water, the rate at which water is leaving this hole, is equal to the velocity it's leaving the hole times the area of the hole. And the minus sign, of course, because the volume of the water in our tank is decreasing. So we can go ahead and write dV dt is equal to negative AV, where A is the area of our hole here. And we also know that if we let capital A of y refer to the cross-sectional area of our tank, then the volume of water in our tank can be obtained by integrating from the bottom of the tank up to a height y, the area function. And so we have this expression for the volume of water remaining in our tank. And so when we differentiate this expression with respect to t, using the chain rule and the fundamental theorem of calculus, well, the fundamental theorem of calculus says if you differentiate this with respect to y, then you just get what's inside, a of y. But by the chain rule, since we're differentiating with respect to t, we get the derivative with respect to y times dy dt. So that's why we have a of y by the fundamental theorem of calculus and dy dt from the chain rule. So a lot's happening here, but in the end we do have this expression for the rate of change of the volume of water in our tank. And we also know, so this we obtained from fundamental theorem of calculus and chain rule, this we got from Torricelli's law, and they're both equal to dV dt, which is cool. So now we can set them equal to each other, and we get a of y times dy dt equals negative AV. But by Torricelli's law, v is root 2gy, so we replace v with root 2gy, and we have a differential equation. And I've put that in a box here for you. You don't have, so we actually were able to figure all this stuff out from fundamental theorem of calculus, chain rule, and this empirical fact up here. Using all those things, we got to this point, and you're free to memorize this if you wish. Usually I would provide an equation like this on one of my exams, but it's an interesting little law. It's a differential equation that relates the height of the water, that's y, the distance from the bottom of the tank to the surface of the water is y. It relates the height of the water to time. So this differential equation says something about how fast the tank will drain. So we go straight to an example now. We have a hemispherical tank with radius at the top of 4 feet. So we have a tank just like this. And let's say that at time 0, the tank's full of water. And at that moment, a circular hole of diameter 1 inch is opened in the bottom of the tank, right here. How long will it take for the tank to drain completely? Let's solve this. Begin by writing Torricelli's differential equation. This is what we had. This is true for any water draining from a tank problems. And let's label the diagram. So what I've done here is I've taken a snapshot, a moment in time, when the water is partially drained, and I've labeled a bunch of things. So the distance from the bottom of the tank to the surface of the water, that's y, meaning that the distance from the surface to the top of the tank is 4 minus y, because 4 is the radius of the tank. And keep in mind, the fact that it's a hemispherical tank is important in this problem. It means that the distance from the center of the tank, well, the center of the sphere, from here to any point on the tank is always 4. Again, we're trying to find the surface area of the water. That's what A of y stands for in Torricelli's law. So A of y is, well, the area, the surface is circular, so its area is pi r squared. We need to figure out what r is, and I've done that for you here using the fact that this is a right triangle, and we know this leg and we know the hypotenuse. So I went ahead and solved for r using a squared plus b squared equals c squared, and solving for this leg. I got an expression for r, which was the square root of 16 minus 4 minus y squared. The reason there's no square root here is because area is pi r squared, and the squared made the square root go away, if you understand. I simplified what was in here and got pi times 8y minus y squared. So I just expanded this and collected like terms to get here. Next, we know that the area of the hole drilled in the bottom of the tank is pi times the radius squared. We're measuring things in feet here. So if the hole had a diameter of 1 inch, that's 1/12 of a foot, meaning the radius is 1/24 of a foot. That's what I did here. So the area of our hole is pi times 1/24 squared, and gravity, since we're working with feet here, is 32 feet per second squared. And the reason I'm working with feet here, I usually don't. I got this problem from Edwards and Penny differential equations with boundary value problems, and rather than change all their stuff, I figured just I would use their numbers. So I did. We're working with feet right now, so this is 32 feet per second squared. So our differential equation, which we had up here, we replaced a of y with pi 8y minus y squared, and we figured that out. Lowercase a, that's the area of the hole, is pi times 1/24 squared. Don't forget the minus sign when doing Torricelli's law. And finally, we have square root of 64y. which, by the way, probably explains why Edwards and Penny wanted to use feet for their problem, because conveniently 2g is 64, which is a perfect square. So you can integrate both sides. Actually, the pi's cancel here, so we don't need pi in our answer. You can just divide both sides by pi, and we integrate both sides, which I've done for you here. 8 divided by 24 squared is 1 over 72. I've done that arithmetic for you. And so we have these two integrals. Let's integrate. And it's just power rule throughout. So the left-hand side is this. The right-hand side is negative 1/72 t. And we add an arbitrary constant of integration, c. Don't forget that. And now we apply our initial condition, which is that the height of the water at time 0 was 4. Recall that the hemispherical tank was full at time t equals 0. And since the tank has height 4, we conclude that y of 0 is 4. Now we can take this whole equation, plugging in 0 for t and 4 for y, and we find that c is equal to this number here, 448 over 15. The tank is empty when y reaches 0, of course. So if we go back to this equation here and plug in 0 for y, we can figure out what t needs to be for the tank to be empty. So 0 on the left-hand side equals this stuff on the right-hand side, where we just figured out what c is over here using the initial condition. So now we're here and we can solve for c. So we subtract 448 over 15 from both sides, multiply by negative 72, and we get t is approximately 2,150 seconds, which is 35 minutes and 50 seconds. A pretty reasonable sounding answer, I would say, for a tank of that size and a hull of that size. So I'll accept that answer, will you? Yes, there's one more thing I wanted to say about this problem, which is that notice that we got here after doing our separation of variables and integrating. And this is one of those problems that I told you we would encounter, where you cannot solve for y as a function of t. And in fact, there was absolutely no need to. We were happy to just leave it in this form, and we were able to figure out the information that we needed, which was when will the tank be empty. We were able to figure that out just fine without solving for y. So these implicit solutions, that's what these are called, are often all you need in the applications. Let's move on. I took the liberty of plotting our solution. Mathematica can do implicit plots. Actually, I made this plot a little while ago, and I've since learned that a better function for this is the contour plot function, just for the record. If you want to know how these Mathematica functions work, just read the documentation, and it'll tell you way more than I could ever tell you about them. I'm really no expert, actually. I just read the documentation and figure out what I need as I go. Anyway, I plotted this equation here. This percent just is this equation, and so this is a plot of y as a function of t, and it looks almost linear for a while, and then apparently the draining rate speeds up toward the end. And disregard, I didn't draw a t-axis, but the t-axis is about here, and you can just disregard this bit of curve here. That's nonsensical. That's negative values of y. So it stops about here, and this raises an interesting question. Suppose we wanted to use a tank of water to measure time. That is, suppose we wanted to fill up a tank with water and let it drain ever so slowly but in such a way that the height of the water was draining at a constant rate, so that you could measure time by just looking at the height of your water. And so the question that I'm asking is, what shape tank would you need such that if you solved the Torricelli differential equation, the draining rate would be constant, it would be linear. And that's called the clepsydra problem, because people have used things called clepsydras to measure time, and but you have to make them shaped just the right way, such that the water will drain at a linear rate, at a constant rate, that is. So that's the question for you to ponder on your own, is what shape tank would you need to make an effective clepsydra? Now this is a great problem. This is the hanging rope problem. We have a rope. It has a length L, and we attach it to 2 points, and then it hangs from there under the influence of gravity. And we are going to figure out what shape the rope makes. If you've seen telephone poles, say for example, we've all seen lots of examples of this where we have some kind of cable or rope and it's hanging, say between 2 telephone poles, and it makes this arc. It looks a bit like a parabola. In fact, you might even conjecture that it is a parabola if you didn't know any better, and soon you will know better. So we're going to actually find a differential equation that will help us figure out what shape the rope makes when it hangs between these 2 points. So our hanging rope, if we look at a short segment of the rope, which I've pictured here, there are 3 forces acting on it. There's a force of tension pulling the rope to the left. There's a force of tension pulling the rope to the right, and there's a gravitational force pulling straight down. I've labeled the forces TL, TR, and FG. And we're trying to track the angle that the rope makes with the horizontal, where we consider the rope to be making an angle of theta here, and then theta plus delta theta over here, as we move over a short distance from x to x plus delta x. So try to imagine this as being a very short segment of our entire rope. And if we do that, letting theta, again, that's the slope, and the funny thing about ropes that are hanging is that they are at rest, and things that are at rest are not moving, and in particular they're not accelerating. And if they're not accelerating, then by Newton's laws, the forces acting on our object, in this case a little segment of rope, the forces acting on our object must add up to 0. So this force plus this force plus this force must add up to 0. So we can figure out what the components of these 3 forces are. The left-hand force is equal to the tension in the rope, which I'm denoting just by T of x. Note that the tension will change from point to point along the rope. So there's one tension here and there's a different tension here. So I'm referring to the tension anywhere by T of x. And so this is the left tension. This is the right tension. Notice that we're measuring the tension at x plus delta x now. And we're using the angle theta plus delta theta instead of theta. And finally, the force of gravity is pretty simple. It's just 0. It's pointing straight down, so the x component is 0 and the y component is negative mg. Now as simple as that looks, actually the mass of our rope well, we need to figure out what that mass is. Mass is equal to the density of the rope times its length. We were going to assume that the rope has constant density throughout. That would be pretty absurd to say otherwise. So we're assuming the density is constant throughout the rope. And the length of the rope, I encourage you to check if we just wanted the distance from, we can say it's approximately the distance from here to here. And just a little bit of trigonometry from drawing a right triangle here where I'm moving my laser pointer. If we draw a right triangle there and use a little trigonometry, we find that the length of the rope of this little segment of rope is delta x times the secant of theta. And so the mass is density times the length of rope, which is density secant theta delta x. Now, the tension, that is the left tension vector, plus the right tension vector plus the force of gravity equals 0, as we discussed before. And so we can add together the x components. The x components have to add together to make 0, and the y components have to add together to make 0. Divide both of these equations by delta x and take the limit as delta x approaches 0. Now the first equation becomes this, and the second equation becomes this. Now this would actually be too hard for me to explain at the moment exactly where these came from. Roughly speaking, I used the product rule of differentiation together with the limit definition of the derivative. I think I'll post a bit more about this on my website, a more thorough explanation of how you go from these two equations to these two equations. It's a great exercise if you want to try to do it on your own. It's also pretty hard. So I believe I will put an explanation of this online. For the moment though, you can take my word for it that you do get these two equations from these two if you do what I said to do here. So these are our two equations that we just found. It's a system of two differential equations in terms of the tension of the rope and the angle that the rope makes with the horizontal. If we look at the first equation and rearrange, we actually see that we can get this just by moving stuff around. And then if we, it turns out there's nothing stopping us from canceling the dx's on both sides. And so what we actually end up with is something like this, which is a separated equation. And we can integrate both sides, and we find that, recall the integral of tangent theta is natural log secant theta, and the integral of dt over t is the natural log of t plus a constant. I called it C1 because we are going to have other constants momentarily. Exponentiate both sides, and that's why I use this little subscript 1 here, is because I was planning on getting rid of this constant. When you exponentiate both sides, you get secant theta on the left-hand side, which now it's the right-hand side, and we get t times e to the c1 on the right-hand side. So I divided both sides by e to the c1, and I called that constant k, and moved stuff around to end up with this expression that you see here, t equals k secant theta, which is a pretty cool equation by itself. It actually tells you how the tension in the rope depends on the angle that the rope is making with the ground, which is already pretty cool. But we're going to get a lot better than that. We're going to find out exactly the shape that the rope makes. Differentiate both sides of this equation. here, you get with respect to x, and on the left-hand side you just have dt dx. On the right-hand side, using the chain rule, the derivative of secant theta is secant theta tangent theta, but by the chain rule, since we're differentiating, I should say, with respect to x, so you get the derivative times d theta dx. That's the chain rule. And then we can insert this expression for dt dx right here, and insert k secant theta right here. And now we're going to have one giant equation just in terms of theta. So this equation here, this second equation, after you make these two substitutions, you end up with this pretty monstrous looking expression. Notice I did some simplifications here. So k secant theta tangent theta times sine theta amounts to tangent squared theta. Think about that for a moment. And this expression here became just, since secant theta times cosine theta equals 1, they actually cancel. You're left with k d theta dx for this second term. And the right-hand side is the same as it was before, rho g secant theta. So we have this interesting looking differential equation in terms of theta. And we can actually solve it. Just factor out k d theta dx, and you're left with tangent squared theta plus 1 on the left-hand side, and that's equal to secant squared theta. So the left-hand side can be rewritten as secant squared theta d theta dx. I canceled the secant theta on the right-hand side and divided by k, and if you do all that, you can go from here to this much simpler equation. Again, the main thing I did was I recognized that we had tangent squared theta plus 1, and that makes secant squared theta. Then I just simplified stuff, brought the k over to the right-hand side, and multiplied through by dx. It's just separation of variables. Indeed, this is a separable equation, and this is what it looks like after we simplify and separate. We can integrate both sides, and the integral of secant theta d theta, you might recall from Calc 1 or 2-ish, is natural log of secant theta plus tangent theta. And on the right-hand side, this is rho g and k are all just constants, so this is really just the integral of a constant dx. So you get rho g over k x plus a new constant, which I'm going to call c2. We can't solve for theta here, and nor quite do we want to yet. Instead, we're going to translate this back into figuring out what y is as a function of x. That ultimately was our goal, was to figure out how high the rope is at position x along the rope. And we want to use the fact that the slope of the rope is just the tangent of the angle that the rope makes with the horizontal. And using a little bit of trig, secant of the angle the rope makes with the horizontal is equal to the square root of 1 plus dy over dx squared. You can get this equation from this equation just using the fact that tangent squared theta plus 1 equals secant squared theta, and then taking the square root of both sides. So this follows from this. Using these two facts and plugging them in here and here, we get this lovely expression. And perhaps you haven't seen this before, but this is really cool. It turns out that this expression you see here, the natural log of the square root of 1 plus dy dx squared plus dy dx, There's a special name for this function. It's called the inverse hyperbolic sine. If you've seen the hyperbolic sine before, which is e to the x minus e to the negative x over 2, it turns out it also has an inverse, and the inverse is given by this equation here. The inverse hyperbolic sine of a number u is the natural log of the square root of 1 plus u squared plus u. So what we have here is the inverse hyperbolic sine of dy over dx. So the left-hand side is now inverse hyperbolic sine dy dx. The right-hand side, so I'm going to take all these constants here and relabel it as capital A. So inverse hyperbolic sine dy dx equals ax plus b. I'm calling this constant b. And now we can take the hyperbolic sine of both sides of this expression to find that dy dx is the hyperbolic sine of ax plus b. So we know this, and it's also a fact that the integral of the hyperbolic sine function is the hyperbolic cosine function. So if we let u equal ax plus b, do this u substitution, and integrate both sides, we can find that y equals 1 over a inverse hyperbolic, just hyperbolic cosine of ax plus b, all plus a constant c. That's just the constant of integration. So the length of this curve from the left side to the right side is given by the arc length integral that you should have learned in Calculus 2. We integrate from the left side to the right side of the square root of 1 plus the derivative squared with respect to x. And if we write out what that is, the derivative of y is the inverse hyperbolic, it's the hyperbolic sine of ax plus b. And then 1 plus sine h squared is cosine h squared. So, and then when we take the square root, that squared goes away, and we're just left with this very nice expression. And the integral of hyperbolic cosine is hyperbolic sine. Doing a u substitution, we end up with 1 over a coming out. It's the same u substitution that we did up here. Anyway, we get 1 over a hyperbolic sine of ax plus b evaluated from the left side to the right side. So we just plug in the right side and plug in the left side. And we get this for our length of the rope. But wait, we already knew the length of the rope. The length of the rope was L. So we've shown that our rope is a hyperbolic cosine curve. We know that the left-hand side, we have these two initial conditions, that y of x naught equals y naught and y of x1 equals y1. And finally, we know that the length of the rope, which we found was this whole expression here, the length of the rope was given to us as L. This is a system of 3 equations in 3 unknowns, a, b, and c, right? Because you need to plug this stuff in here, and let's just show you what that is. For example, if so now I'm going to give you a specific example where the left endpoint is at negative 5, 0, the right endpoint's at 5, 0, and the length of the rope is 15 meters. These equations become this, and this. These 3 equations become these 3 equations. And if we solve them by computer, we get these numerical answers for a, b, and c. So we conclude that y, which is 1 over a hyperbolic cosine of ax plus b plus c, putting in these values of a, b, and c, we get this expression for y. And if we plot it, we get this thing. which is looks like a parabola, you might say, but now we know it is a Catenary curve. It is a graph of the hyperbolic cosine function. So we'll move on to a pretty different type of application here. This is the falling satellite problem. We have a satellite. It is pretty far from the moon, and it's traveling toward the moon pretty fast, 1,200 meters per second. And we want to predict the time that the satellite will strike the moon and the speed it will be traveling at that time when it strikes the moon. We're going to ignore gravitational effects from all objects except the moon, so we're just going to assume this is a simple situation where we just have an object and we have the moon, and we'll ignore everything else in the universe but these two objects. And it still makes for a pretty interesting problem. First of all, I looked up the radius of the moon for your convenience. Here it is. And we have the following equation from physics, that the force acting on our falling object is equal to its mass times its acceleration. And since we're assuming the object is falling straight toward the moon, we're just going to track its y coordinate, its distance from the moon. So and acceleration is just the second derivative of position. Now the only force acting on the satellite is gravity, and gravity is given by one of Newton's other very famous equations. The force of gravity is equal to minus the universal gravitational constant g times the mass of the planet or larger object times the mass of the smaller object, divided by the distance that the object is from the center of the larger object squared. So you might have heard before that Newton's law of gravity is that it's inversely proportional to the square of the distance between the two bodies. The mass of the moon I've also looked up for your convenience. This is the mass, lowercase m. The mass of the satellite actually is irrelevant, as you'll see in just a moment. And capital G, this is the universal gravitational constant, not to be confused with lowercase g, which is Earth gravity at the surface of the Earth. This is the universal gravitational constant. It's a pretty tiny number, times 10 to the minus 11th. And y is the distance from the satellite to the center of the moon. So we have two expressions for force. Newton's gravitational force equation and Newton's F equals ma. Put these two things together, we get this. I mentioned before, the mass of the satellite does not matter because we can cancel the lowercase m's from both sides. So we will do that in just a moment, but first we do a pretty famous substitution. This is a really nice substitution that can simplify differential equations when they have second derivatives to turn them into nicer separable first order differential equations. So let v equal dy over dt. Now that's not really anything clever, that's just the definition of velocity. Velocity is the derivative of the y coordinate with respect to time. But now we do something really clever here, is we notice that the second derivative of y with respect to t, y prime prime, is just the first derivative of v with respect to t, right? Because v is already the first derivative. V is y prime, so y prime prime is v prime, which is dv over dt, which by the chain rule is dv over dy, dy over dt. And then we make yet another fantastic observation. Look, here's dy over dt, and that's nothing else but v. So that's this blows me away still, and I've seen it 1,000 times already. Y prime prime equals this through this series of clever observations. Worth remembering, I might add. So we go ahead and make that replacement. First of all, I went ahead and canceled the lowercase m's on both sides, and I replaced y prime prime with this new expression, dv over dy times v, so that's this. And the right-hand side is this. So now we're actually solving a differential equation where v is a function of y. Velocity depends on height, which is pretty cool because the differential equation started with y depending on time. Now we're talking about velocity depending on y. So we've actually changed variables here. I'll never expect you, if you're in my class, to be this clever by yourself on an exam or some sort of thing like that, but I do want you to be aware of these clever substitutions that can be done. So this equation was transformed into this one using this series of substitutions. This is a separable equation. V dv equals negative gm dy over y squared. We integrate both sides. Integrate both sides, we get 1/2 v squared equals gm over y plus a constant of integration. Notice the minus sign went away when we integrated, which is cool. And now we use our initial conditions. Recall that the satellite was traveling toward the moon at 1,200 meters per second at time 0. Since we're not talking about time here, the velocity was 1,200 meters per second when the satellite was at this height. So our initial condition is really v equals negative 1,200 when y equals the initial y value. So we can plug these numbers in for y and v to figure out what c is. And noting that v naught is 1,200, capital G is the gravitational constant, capital M is the mass of the moon, y naught is the initial height from the center of the moon. I plugged all those numbers in and I got this number for c. And we conclude, if we solve this equation for v, we get v equals this. The minus sign makes perfect sense. The satellite is falling toward the moon, so its y-coordinate is decreasing, meaning that velocity should be negative, so that's fine. And v is dy over dt. So we note that, and now we have this equation. We have this equation now, and it's another differential equation that we need to solve. So it's a separable equation, so I went ahead and brought all this stuff over to the left-hand side and brought the dt over to the right-hand side. This is a pretty hard integral to do on the left, so I let a computer do it for me. This is what it looks like when you let Mathematica do your difficult integrals for you. Sometimes your answer might be a bit ugly, but we can work with it. Notice that I was allowed to let I was allowed to keep my g, m, and c in the expression. So Mathematica is perfectly happy to integrate as long as you tell it what variable with respect to which you are integrating. So I did tell it to integrate with respect to y right here. So it knew that g, m, and c were constants as far as this integration was concerned. So I got this expression, which I took the liberty of copying on the next slide. So here is that expression that Mathematica got for us when we integrated. So we have all this equals t plus c2. Where this capital C in this on this left-hand side, that's the we already calculated that value earlier. It was 200 and something thousand. The initial conditions tell us that y starts off at 1.390 times 10 to the 7th meters at time 0. So if you plug that number in for y, here, 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 and here, and 0 for t, you can calculate C2, and you find C2 is equal to 218,871. And finally, we want to figure out when impact occurs, when the satellite hits the moon. Recall that y measures the distance of the satellite to the center of the moon, so it will hit the moon when its y coordinate is equal to the radius of the moon, which the radius of the moon is this. So we plug this number in for y, here, 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 and here, and subtract C2 from both sides, and we calculate t. Find that the time of impact t is 8,286 seconds, which is 2 hours, 18 minutes, and 6 seconds. That is the time that it will take the satellite to fall toward the moon and hit it. And at that time, earlier we calculated that velocity in terms of y is equal to this expression. And y is just the radius of the moon, so 1.737 times 10 to the 6th. I put in for y here. Universal gravitational constant, mass of the moon, and the value of c that we calculated earlier, and you end up with this velocity of impact. So it's going to crash pretty hard, not surprisingly.